Have you ever just stared at a circuit diagram and had absolutely no idea where to even begin? Well, in the next few minutes, we're going to open up a powerful toolkit that will let you solve pretty much any circuit you come across, especially the ones that look impossible.
So, take a look at this. It's a classic complex circuit. The components aren't in a nice simple series or parallel arrangement. You know, your basic tricks. They're not going to cut it here. It looks like an unsolvable puzzle, but I promise you, it's not. You just need the right tools for the job. So let's think of circuit analysis like having a real toolbox, right? You wouldn't use a sledgehammer to hang a picture frame. Today, we're going to fill that box with everything, from the absolute foundational laws to the really specialized gear you need for those tricky situations.
Okay, before we start grabbing all the cool power tools, we need to understand the two fundamental laws of physics that everything else is built on. I mean, these are the unbreakable rules for every single circuit, period. First up is Kirchhoff's current law, or as we all call it, KCL. This one is all about the nodes, you know, the points where components connect. It's based on the conservation of charge, and it's super simple. The total amount of current flowing into a node has to equal the total current flowing out. What goes in must come out. Always. And its partner in crime is Kirchhoff's voltage law, or KVL. Now, this law applies to any closed loop in a circuit. It's all about the conservation of energy. It basically says that if you take a walk around any closed path and add up all the voltage gains and drops, you'll always end up right back at zero when you get to your starting point.
So let's just put them side by side. KCL is all about current, and it happens at the nodes, the connection points. This makes it the perfect foundation for a technique called nodal analysis. KVL, on the other hand, is all about voltage, and it happens in loops. This leads directly to another technique called mesh analysis. See, two laws, two very different jobs, and they unlock two incredibly powerful techniques.
All right, now let's grab our two workhorse tools. Seriously, these are the systematic methods you are going to use most of the time. One's built on KVL, the other on KCL.
So first, there's mesh analysis. This is just KVL in action, really. What we do is identify all the simplest loops in the circuit. We call those meshes, and we imagine a current circulating around each one. Then we just apply KVL to each of those loops, which gives us a nice set of equations to solve for the currents.
And the other path, of course, is nodal analysis. And as you might guess, this one is built entirely on KCL. Here, we focus on the connection points, the nodes. We pick one to be our reference, our ground, our 0-volt point, and then we just use KCL to write an equation for every other node. And that lets us solve for the voltage at all those key points.
But you know, life isn't always that simple, right? What happens when a circuit doesn't play by the standard rules? Sometimes you get a weird case that just jams up regular mesh or nodal analysis. And for that, our toolkit needs a couple of special adapters.
So here's a classic curveball for mesh analysis, a current source that's just floating between two meshes. You can't write a KVL equation through it because you have no idea what the voltage is across it. So, are we stuck?
Nope. The solution is the supermesh. It's a clever trick where we basically just ignore that problematic source for a second and create one big loop around the outside of both meshes. That gives us our KVL equation. Then, we just need one more simple KCL equation at a node to relate the two mesh currents back to that source. And just like that, problem solved.
Now, nodal analysis has its own little kryptonite, a voltage source that's stuck between two nodes, and neither of them is our ground reference. Now, you can't write a normal KCL equation for these nodes because you don't know how much current is flowing through that voltage source.
And the solution here is the supernode. It's the same idea. We just mentally combine those two nodes into one big supernode and write a single KCL equation for everything entering or leaving that entire area. Then, a second super simple equation just relates the two node voltages. It's a really elegant way to sidestep the problem.
You know, sometimes the smartest way to solve a puzzle isn't to attack it head-on. It's to change the puzzle into something you already know how to solve. And our toolkit has some seriously clever tricks for doing just that.
One of my favorites is source conversion. It's this fantastic trick that lets you swap a voltage source with a series resistor for an equivalent current source with a parallel resistor, or the other way around. Doing this can sometimes dramatically simplify a circuit and make the rest of your analysis way easier.
But that brings us right back to our original nightmare circuit, doesn't it? That tangled web of resistors in the bridge. None of our standard methods can really get a foothold because nothing is clearly in series or parallel.
we need to do something more drastic. We need to physically transform the circuit itself. And here is the magic wand to do it, the delta to star conversion. This is a formula, a recipe, that lets you take a triangle shape of resistors, we call that a delta, and replace it with an equivalent Y shape, which we call a star. It looks complicated, but it's just a recipe. You just follow the rule, and you can literally reshape the circuit's geometry.
All right, deep breath. Our toolkit is full. We have our fundamental laws, our workhorse methods, our super adapters for special cases, and now our transformation tricks. Let's go back to that circuit that looked so intimidating at the start.
And here it is again, but this time, it looks different, doesn't it? You're not just staring at a mess anymore. You're looking at it like an analyst. You can see the patterns. You know what tools you have. So what's the first move?
That's right, you spot it immediately, that triangle, that delta formation, right at the top. We're going to grab our delta to star conversion tool, apply that recipe, and reshape the problem before we even try to solve for anything else.
And just like that, poof, the entire structure changes. The roadblock that was stopping us is just gone. What was a confusing tangle is now a beautiful, simple layout with clear series and parallel combinations. It's almost easy now.
And from here, the rest is a piece of cake. You can use your most basic tools, good old Ohm's law, KVL, KCL, to find any current or voltage you want. The impossible problem has been completely conquered.
And really, that's the whole point here. It doesn't matter how complex an electronic device looks, whether it's your phone or the entire power grid, it's all governed by these same fundamental rules, and it can all be understood with the right toolkit. So the only question left is, what will you choose to analyze next?